Just making a draft science video. Yeah, just a conversation about two subjects probably, but maybe more. See how it goes, where I go. So there has been some mention of E equals mc squared, Einstein's energy law, I guess you call it, or mass law. I mean, it's just basically saying E equals m, that mass in and of itself has energy. And I guess I would argue that it doesn't really, in and of itself, that it's a phenomenon consistent with what happens when mass is in the form of atoms. But when the mass isn't in the form of atoms, the mass probably doesn't have this quality of energy, in the sense that mass can be quite useless. I mean, it can be doing nothing, minding its own business, in a sense, in a in the field of things. It can be not disrupting anything, and therefore it can't really be called energy. Sort of, mostly. So it goes back to, well, starts with the way I would restate an understanding of what gives mass energy. And and the other subject will be the right hand rule, just to let you know. So if you want to skip to that, fine, or not. Or maybe I won't get to it. It doesn't really matter. Anyway, alright, so as I have pointed out, I think the universe is made out of two kinds of things, bits of matter and bits of energy. And the energy bits are the only things moving, and the matter bits move, but they only move because they're being pushed by energy bits, and they absorb them essentially. So the energetic things, the moving bits, see, M would be nice. You could say moving bits and not moving bits or something, some other way to describe it. And as I've pointed out, the key to the whole thing working is not just having matter and energy, it's having them polarized, or in two forms. And for the two forms of matter, there are two forms of energy. So we would call this a proton, let's say, and this would be the electron. And this would be electron energy, this would be proton energy, however you want to put it. And they inversely react to each other, in the sense that if a red bit of energy hits a electron, a proton energy hits electron matter, reacts the same way as proton does to electron energy. So there's this inverse relationship, and if the same type hits, it ends up being a reflection. So I've sort of been over that. I don't know if going over it again. I guess it's important because it gets to the drag subject, which is also interesting. So there are the two properties would be, if now I'll draw the force bit smaller. If a bit of red stuff hits a proton, it reflects, in the sense that just it reflects. It comes in and it just bounces back, and essentially. So there's a real transfer that takes place inside the proton, but the only thing you really need to know is that it is something goes in, something comes out, and the whole equation is just there. That's all there is. The proton itself is only moved while it possesses the bit of energy. So if it gives it back immediately, it's just a reflection. If it holds it, then it doesn't give back anything. So it just depends on whether there's place for this proton, I guess in this case proton, to go. But the idea is it's reflection. So the red gets reflected off of the proton in most atomic circumstances because the bits can't go anywhere. They're forced to stay around. So they reflect, and when it's in the form of atoms, I really didn't intend to go in this direction. Then if the black force hits a proton, it just is deflected 90 degrees in one of the planes of 90 degrees, left, right, up, down. to be decided by other conditions, but it just ends up going perpendicular. And there's no energy transfer again. There's just a transfer of direction. And there's no possession. The black bit can't be held by the proton. It can only be deflected. So there's no momentum, just a change in direction without any other change, just the way the universe works. And that provides a solution to the drag problem, because you can change direction by hitting an opposite force, and by changing your direction you can basically do a U-turn and completely change your momentum, and therefore overcome obstacles, because you can trap energy that has one direction to it. It only goes in one way, and it just keeps going that way more than it goes the other way. So the trap word is the key word. That's the word I wanted. It's the kind of the concept I wanted to get to through this process. All right. So when it comes to the E equals mc squared stuff, the point to be made is that if you just had matter in a form like an electron and a proton, they don't do anything. Like I said, just sit there. It's not. They can't. They're not divisible. They don't break into something. You can't pull any energy out of them. So in a sense, their mass can't have any meaning as being energy. But the real point is if you arrange them in an atom, that what you're really doing is trapping them in configurations. And I just use 4 for this example, where there's lots of little bits of pressure, energy, the force bits moving the speed of light between the objects, and that pressure that's holding these that's kind of giving this atom structure, because without this pressure between the electrons would just move into the absence of energy that would exist between the proton and the electron, because all the black energy would leak out, all the red energy would leak out of the electron, all the black energy leaks out of the proton, and would end up being a neutral. So by different configurations of these bits, the point would be is that what an atom does is that it takes the energy from the environment. I don't know how to best illustrate that except for arrows. And it traps some percentage of what goes in, stays in. So inside the atom, there's a net gain in what you could just say these arrows. If you just thought of the energy as quanta of movement, it traps that movement inside of it in circular paths that could just be square also. It could be just back and forth. They're trapped in places where they can't get out, and that is the E equals mc squared idea, is that for an average amount of material bits, that an average amount of electrons and protons inside of atomic structure, the periodic table, you could make the argument that there is an amount of energy that has been trapped inside of that atomic structure in the form of stuff being bounced back and forth, stuff that was free in the environment, and it went in and it didn't come out. So like the Roach Motel, it's stuck in here. And there's patterns here in between the protons and the electrons. So there's places where all these little bits of speed of light energy is trapped inside of the atom. So the net effect is that you end up with a m equals this force that it's always going to take to keep this stuff from collapsing into itself. Now, the thing that stops electrons and protons, and even electrons and electrons, from sticking to each other is kind of obvious. For the electrons, they can't stick to each other because there's always energy going back and forth between them, gets trapped, and there's pressure. So the closer they get to each other, the higher the pressure, so you're just not going to be able to smash them together. And then for protons and electrons, the catch is that although a lot of the energy escapes, most of the black energy, the red energy would escape out the electron, and the black force would escape outside of the proton, so you can't gain any reflections back and forth. You can't trap any energy between them. But the catch would be, is just as this energy went out, new energy could come in. So a bit of red energy from the field could go into the electron and be diverted towards the proton and reflect back, and be diverted to another electron, then bounce back and then come back in. And so there's still some energy. So they'll never clump in a significant way. The only way they can clump is to have closer than usual proximity, which would be something like the nucleus of an atom, where you have the proton and then you have the neutron, which is this collection of a proton and electron. And then you have a proton here, let's say. You can sort of understand these two protons are much closer than they could be together if they were in free space. If two protons were in free space, it'd be a bunch of reflections, but all the reflections are leaking out of the electron. So they can only get so close. And again, the electron can only get so close to the proton, so there's always some space between things, so they can never get too close to each other. All right. So the point I just wanted to make on this subject was that E equals mc squared was always seemed a little bit like a guess or an approximation, a vague thing. I don't think anybody really thinks Einstein knew that if you square the speed of light, that creates the proper number of quanta to establish how much energy or mass value anything you can measure in mass would have. It's just sort of like, he's just basically saying there's a lot of it by c squared. C squared is sort of, doesn't really have anything to do with the equation. It's just a constant thrown in to give it some sort of boundaries. So he's basically just saying a lot by saying c squared of quanta of energy that would be inside of, say, an atom. But there wouldn't be any quanta, there wouldn't be any c squared amount of energy in just an electron minding its own business. It hasn't trapped anything. So all it has is the vacuum energy, and energy is really a concept where you only have energy when you have imbalance. So you have to imbalance a system to have energy. If you have the same amount of pressure on the inside as you have on the outside, you don't have anything that looks like energy. Energy looks like when there's a difference. So, and obviously there's no difference for the electron. It's not making anything change in the environment until you give it something to interact with. And then it can trap between it, or it can actually reduce pressure, which is have a kind of a negative energy value. But that's a whole different subject that's probably best not to play with here. All right. So the other subject that is interesting, I have been thinking about but haven't resolved, but I just thought I would play with it a little bit more. I don't know if I have any notes relevant to this. Look at my bad notes paper. Let's see, only reflects when pressurized. Yeah, so anyway, the whole idea of how this came up with the inducting loops, and with the whole Professor Lewin controversy thing. About the idea of two voltages in one place and the inductor and blah blah blah, just nonsense. But it has to do with coils of wire, and and then when you put a piece of iron inside of the coil, and you make it 1,000 times more magnetic and all that kind of stuff. But it really just has to do with how the wire expresses this faculty, this ability, the right-hand rule. So I guess they probably have like right-hand rule. Now, I don't know why they just don't call it the screw it in, screw it out kind of thing. I mean, it obeys the same rules of putting a bottle cap on or taking a bottle cap off or something. So I don't know why they made it more complicated by talking about doing this right-hand stuff. So the idea is if there's a current flowing into a wire. So let me see See, it's all going to be about how you illustrate this stuff in some respects, because that's the real complexity of it. So you have a current going this way, which now just messes everything up. Is as soon as I say a current going this way, what that really means is a voltage going this way. And it just, so now it's the opposite rule if I use the voltage, because the voltage is the thing they should be using. So it just makes it more confusing, because now they're saying this is the plus end, and then this would be the minus end if the current's going this way. And then it's going to be, if it's going this way, then this is going to be clockwise around this way, the magnetic field. Now, the magnetic field doesn't turn, it doesn't do this. This is why this is just so deceptive to draw it this way, because what they're really talking about is which side of this thing, how does this thing express its magnetism. So it's going to become magnetic. So this is plus minus, and then this is going to become north-south in a sense across this face. And so the way I thought I've attempted to illustrate it is, so if the current is going into, so we have the arrow going in, which means the point is used for the arrow coming out, and then you use what do they use? I guess they just use the plus sign or whatever, a little asterisk maybe. Oh, that's the arrow going in. Anyway, so it's going in. Then so that's the current now again. So again, it's just so backwards, because the voltage is the opposite. So that's saying that the current going in is saying that we're plus here and that we're minus down here somewhere where this goes. So anyway, the point would be, so now this is going to make this so much more difficult. Now I'm thinking in terms, I have to think in terms of voltage to make my point. So the point is that if it's going in, okay, then we know it's going to be, okay, so that's the current going in is going to be clockwise. So that would be the opposite of the right plus and minus. So the idea would be is when there's a current moving through the wire, what's happening is that the magnets are going to decide the right and left hand rule. So if you just thought of it like when current goes in, it essentially pops magnets up. And the idea is they go all the way around. So, and the only thing that matters is that you can sort of understand that they have an edge that sticks out. So like the next magnet would be here. And just so you can get the idea that this red force would be seen from this side, and the tail end, the black force, would be seen from this end, because it would be leaving, but they're not moving. So it's just what they're revealing as a profile. So if you thought about like current goes in and the magnets pop up, and that's the magnetism. So while you have pressure in the wire, and this is just an analogy. I'm not saying it happens this way. I'm just saying that essentially what's happening is little magnets pop out of the wire, and that's the effect of it. And then you could understand why two wires that have current going the same way, that is, if I put two wires with current going in both of them, they'll both end up having red-black, and you'll see that means that the red end will be facing the black end, and that they'll end up being attractive. There ought to be a symbol for attraction, some sort of, like repulsion would be drawn like this, and attraction would, there needs to be a symbol for that. Some sort of, maybe a converging thing like this, if the lines are converging that way, or the lines are converged this way, one would be attraction, one would be repulsion, some kind of, there needs to be some kind of better way to illustrate this. So anyway, so this answers the kind of paradoxical circumstance where you have two like things next to each other, and they're attracting instead of repelling, because likes are supposed to repel, like electron. But they're only doing that because of this fact that if you arrange them identically, they'll be looking at each other's reflections, so the wrong face will be facing the wrong face, and so in a sense they're opposite, because they're the left and right version, or however to say that. So anyway, so there's a reason for this rule, and I don't know what it is. I haven't figured that out yet. But it's a simple little rule, right? That every time the current goes in, it's red, black, and then if the current's coming out, it's, red, black. So, I mean, it changes direction. The magnets are the other way around, depending on which way the current is. But that's basically the origins of the right-hand rule. This is why the rule exists. And so when you have a loop of wire, the trick is to think of it that I probably should leave little ends here. When you're spiraling around, that the surface of the wire, no matter which way you go around the wire, so no matter which way I look at this wire from whatever angle, it'll always look the same, and it'll always look like red end, black end. It'll be red end, black end. It'll always be left side will be one, the right side will be the other. And so in a loop of wire, the same thing is happening. So the forward, the inside this loop edge is like the red side of the magnet, and this side of the wire will be the minus side of the wire, the north-south line. And it just does that all the way around, and so it's like a little magnet. And then the whole loop, magnetizes, so you can just keep going inside the loop. The whole loop ends up just keeps doing that same magnetic configuration. So it's a bunch of magnets lined up, essentially, creating one. The idea would be it would be one big magnet in the end for the loop, and it would be a magnet, north-south or whatever the right direction is, but that's what it's doing. So the loop curling this way is just imposing a bunch of little magnets, little bits of magnetism that are all in the same orientation, so all the magnetism points in one direction, so that's why it just becomes one big magnet. So because the side of the wire, this side is saying South Pole, this side is saying North Pole. No matter where I turn it, that's what it's saying, And so that's what's responsible, in my opinion, for the right-hand rule. And now the question is just how does magnetism generate that? How does electricity force that to reveal itself? And then there's the other catch, which is also interesting. And the other phenomena, the other way to provoke this magnetic response, but in a quite a different way, is hitting the conductor with charge. So if I expose it to a magnetic field, an uneven magnetic field, that is a field that's producing more pressure than normal. So the normal amount of the field produces a certain amount of pressure. Now if I use using magnetism, you can change the percentage. So the field percentage is half and half, red and black, and I can change that percentage and end up with something that's more black and less red, or more red and less black. But the key thing is really how much black, because the black is what's going to be affecting the electrons most overtly, in the sense of either pulling electrons in one direction or pushing them in another. Now the pulling part is actually pushing, but we don't want to get into that. And so in a sense, we're back to changing the shape of the atom. So the atom on the surface is basically being flattened, let's say, by the pressure, and so the electrons are now obscuring the protons because they're being pushed, ironically, closer to the proton, but in a sense, by being moved closer, it's like moving the moon It's like moving the Earth closer to the sun, let's say. You would end up creating shadows to the other planets. You'd be blocking the sunlight. And vice versa. If the electrons move away from the proton gets stronger because now you're casting less of a shadow. And so it's basically, this is changing the atom into a charged element. It's not really a full magnet. By default, it ends up being a kind of dipole, but in a sense, obviously it's faced towards the world, that is, the world looking at it. It's charged. It's just one or the other. It's either negatively biased or positively biased or neutral. And so it's only in the presence of the field does this flattening happen. So there has to be a bombardment of it, and it has to be a changing field. So the idea would be is that whatever happens to these atoms, they have to be able to be, once they're in a state, they have to stay in that state till something changes for them to change into another state. So once they're pushed into a state, then they rebalance in that condition. That is, eventually the proton moves back, okay, because the electrons move towards it. Or you could say the whole atom readjusts. But the point is that the atom readjusts. So we're really just talking about how long does it take an atom that gets compressed, how long does it take it for the proton to adjust to the new position of the electron. So if I move the electron, like there's a standard distance between, I'll just draw the same color, between the electron and the proton. The idea is that the electron can move and the proton doesn't move right away. It takes it a little bit of time. And that's the time you have while this will be magnetic. But by the time the electron does act, then it's back to being neutral again. And so you have to repressurize it. But even that isn't quite right, because obviously you're exposing it to a constant field. So it's not that you have to repressurize it; it's that it's balanced to the new condition. The proton moves, the electrons stay where they are. It's pressurized, and until you depressurize it, it can't do anything else. It's just going to stay that way until you relax it. So that's why alternating current works so well, is because it imposes the pressure and then takes it all away again, so it can impose it again, and then take it all away again, and impose it again. So that's the better stated version. And obviously, what's happening too is this pressure is being felt by all the atoms, and so it induces a current. So there ends up being a bunch of atoms that are have more pressure or less pressure. So the less pressure would be the bigger ones, the smaller ones would be the higher pressure, and they're going to transfer that pressure to each other. So the small one will hit the big one, and they'll both become neutral, and then they'll go, and so there has to be a constant supply for it to keep running through a system. So the neutrals, I don't know, I should have drawn them three sizes, I suppose. Well, neutrals will just make solid. So you sort of understand that the pressure will just move through a neutral field very well, but pressure can't move through pressure. So two atoms next to each other who are pressurized, they can't go anywhere. But again, we're back to a right-hand rule. For some reason, the high pressure always moves in one direction. And that's the thing that needs to be explained. Why the preference for one way is always high pressure, one way is where the low pressure goes. And another way of putting that is how they polarize. You could say that's what it is. Decides which way the magnet is. So red, black, and that's sort of being decided by something in the nature of things that says it always goes. It always does this left to right thing. For whatever cause we want to say, it always goes right. It never goes left. Something like that. All right, so those are just things I've been thinking about. So that's it. Yeah, nothing elaborate. just a musing kind of video. No, whatever. I'm just saying this, the elements of a good theory are right here, I think. So it's clearly, it makes sense. And it's just putting all the ducks in a row. It's just a matter of time and such. So I think I'll end there. And I just, I got so many, just too many things to do. It's experiments I want to do, lots of stuff, and just can't organize the time for stuff. Anyway, till next time and such.